In the previous several lectures, we discussed a concept in quantum mechanics known as Heisenberg's uncertainty principle, which basically comes from the dual nature of matter. The fact that matter can act as waves or it can act as particles. So now let's actually apply that principle to solve the following example. So an electron is traveling along the x-axis with a constant velocity of 2 million meters per second. Now, if the velocity of the electron is measured to a precision of 0.15%, we want to calculate the maximum accuracy with which the position of the electron can be measured at the same instant in time. So we're assuming the mass of the electron is equal to 9.11 times 10 to negative 31 kilograms, and our constant h bar is equal to 1.055 times 10 to negative 34 joules multiplied by seconds. So basically, this example is a direct application of Heisenberg's uncertainty principle that relates the uncertainty in position of our electron with the uncertainty in momentum. So basically, it tells us that the uncertainty in our position of the electron along the x-axis multiplied by the uncertainty in the momentum of that electron along the same x-axis is greater than or equal to h bar, our constant. So basically, from the information that we're given, we can calculate what the uncertainty in our momentum of that electron is. What we want to find is the uncertainty in our position of the electron, knowing this quantity. So let's take this equation, rearrange it, and solve for delta x. So delta x, the uncertainty in our position of the electron along the x-axis, is greater than or equal to h bar divided by delta px. Now, what exactly is momentum? Well, if we're dealing with non-relativistic momentum, then the momentum p of our electron is equal to the product of the mass multiplied by the velocity. Since we're dealing with the change in momentum p, this is equal to the mass, which is constant, multiplied by the change in velocity of our electron. So let's replace delta px with the mass of the electron multiplied by the change in velocity along the x-axis, also known as the uncertainty of the velocity of our electron. So if we take the uncertainty in velocity of the electron and multiply it by the mass of the electron, we get the uncertainty in momentum of that same electron. So let's plug in our h bar, which is equal to 1.055 times 10 to negative 34 joules multiplied by seconds. We divide that by the uncertainty in our momentum. So the mass of that electron, 9.11 times 10 to negative 31 kilograms, multiplied by the uncertainty of the velocity. So 0.0015 multiplied by the velocity of our electron. So this quantity gives us the uncertainty of our velocity of that electron, and this entire denominator, if we multiply this by the mass, that gives us the uncertainty of our momentum of that electron along the x-axis. So from this calculation, we see that delta x is greater than or equal to 3.86 times 10 to the negative 8 meters. So we see that the answer is the maximum precision with which the position of the electron could be measured at the same exact instant in time for this particular velocity, and this particular precision for that velocity is equal to 38.6 nanometers. So by the uncertainty principle, the best simultaneous position will have an uncertainty of 38.6 nanometers along the x-axis. So basically, if we know the uncertainty of the momentum of our particle, which is equal to the product of these three numbers, the uncertainty in the position of that same particle, that same electron along the x-axis, is equal to this value.